Hello, everyone. Welcome to the third video in our series, Building Protein Transformers from Scratch. So in the previous two videos, we have established our data set, and we've built a very simple probabilistic neural language model to predict and generate new protein sequences based on a 2003 paper. In this lecture, lecture 3, we're going to expand that protein modeling architecture to use a transformer. And in particular, we are going to implement a decoder-only transformer model from scratch in the notebook to show that there's really nothing scary going on in there. And again, we're going to follow the footsteps of Andrej Karpathy's amazing series, Neural Networks Zero to Hero. And so we'll use a lot of the same tricks and a lot of the same vocabulary. If you haven't watched Neural Networks Zero to Hero, I highly recommend that you watch that series. In particular, Andrej does an amazing job during his lectures at building up the concepts for the transformer, kind of step by step. So you can see in code the progression from like a bigram language model to a transformer model. Here we're going to skip a lot of that context because those models are not particularly useful in modeling proteins, and we're going to jump straight to a protein transformer architecture. So another thing we're going to do in this video is we're going to sort of encapsulate and modularize our implementation using best practices in PyTorch. Along this video, we're going to be thinking about sort of three main papers. So the first one, the original transformer paper, Attention is All You Need. The GPT-2 paper, and then the GPT-3 paper as well. The GPT-2 paper was a little bit light on details, and so we're going to use a lot of the details from the GPT-3 paper in building our transformer model. We're going to build a transformer model that is identical to the model in GPT-2. This keeps things really simple and straightforward for us, and allows us to sort of cross-reference with a lot of the fantastic NLP literature, keeping in mind that we have a very different problem, right, when we're modeling protein sequences. Okay, so let's dive into our implementation. So in the previous notebook, we in lecture 2, we read in our data set and we built a simple probabilistic language model in PyTorch code. In this case, we're going to rely more heavily on pre-built things, and so we're going to add to our imports here. So let's just go through what all these imports are. Math and random from the standard library. Data classes from the standard library. It's a super useful tool that allows you to build lightweight Python classes that act as data holders. Can keep things really clean and organized in your code, recommended. Again, we're going to use Biotyte, and then we're going to import some data handling things from PyTorch. Again, we're going to set manual seeds right up top here, so everything in the notebook is reproducible here on this computer and also on your computer. We have to set both Torch and the standard library separately, so we'll do that right here. Okay, so what's the first step in our pipeline here? So we need to be able to represent our data for the transformer model, and the way we do that in PyTorch land is we create a PyTorch dataset class. So this dataset class, it may look a little complicated, but really there's really only 3 components to a dataset class in PyTorch. One is the init function, and that will basically take whatever data you have on disk or elsewhere and create the representation internally to the class. Then there's the length attribute. Well, this just returns the length of the dataset. And then there's the get item method. And this method just returns a single sample from the dataset. And so this is just a really clean, consistent interface that PyTorch uses for all the data sets that we're going to follow along with. These other things here are just sort of for our own convenience. But let's walk through those three main parts of this data set. So rather than sort of just build the data set up sort of in bare Python, we're going to build this class first and then use this to read in our data. So the init function takes a list of proteins, a list of characters, and the max protein length, and does something very similar to what we did before, just builds a very simple tokenizer. Because we have read in all our proteins, we know how many examples are in our data set, and the length function can just return that number. And then the real magic happens in this get item function. So this is just adopted from our code building up our data set. Again, this takes each individual protein and builds up training examples. So previously what we were doing is we were taking 3 amino acids and predicting the next one. But these natural language models that we're going to use here, the transformer, can use the whole sequence, and we really want to use that. But the language model still benefits from all the little examples packed into each protein sequence. And so what we're going to do here is we're going to build up training examples for every character in the sequence so that the model can learn to produce sequences of different lengths and has a lot more training examples to learn from. So in particular, we take our protein sequence, we turn it into a list of integers, and then we create sort of 2 new tensors. One is the input data, the list of integers, and then the next one is basically the same list of integers shifted over 1. And so why do we do this? It's because the model is going to predict the next character from all the previous characters. And this is just a really clean way to build up all those training examples at once in this data set. So let's look at an example of using this. So let's just start with some very, very simple protein data. I just made up some protein sequences here. They're all really short. This is the list of protein, this is the list of amino acids. And then I'm just going to provide the maximum length here, which is 38 for these sequences that I created. And we can create our data set by passing in the proteins, the vocabulary, and the max length. And then from our data set, let's just do that here. And then from the data set, we can index into the data set to pull out training examples. So in particular, let's look at the first training example here. So this is a protein represented as integers. And we can see that the first character is our padding or our start character, the dot, which we represent with a 0. And the remaining characters are all protein amino acids. So we can already recognize some of these that we remember from the last lecture, like alanine is 1. So here's a couple of alanines. And then let's look at the y vector, or the vector that our model is seeking to predict. So you can see that for every span of characters, let's take the first 3 here, the character in the y vector at that same position is the next character in the sequence. So the first is 0, 11, 2, and then we have 10 here. Similarly, 0, 11, 2, 10, and then we have another 10. 0, 11, 2, 10, 10, and the next one will be 16. And so this is just a really clean way to map our data set into these training examples that our model can learn from. So now that we have sort of the logic for creating a data set, let's wrap this into a nice function that reads from a FASTA file. So again, all this code should be extremely familiar. This is the exact same code that we used previously. Just basically indented it and put it into this function. And then added these lines here where at the end we create 2 dataset classes, one for our training examples, one for our test examples. And we can now read in our dataset and use the creates dataset function that we just wrote to build these protein dataset classes up for our training and test sets. And once we do that, we can look at an individual example. So let's just read through this, make sure it makes sense. We split the data set up into 24,000 training examples and 2,600 test examples. This is the total number. The vocabulary is the same as before. The number of unique characters is the same. The total tokens is also the same. It's just over 2 million. And let's look at the first pair of X and Y from our training set. So here's the X. We can see here it starts with a 0, a padding token, start token, contains our protein tokens, and then we can see that the rest of the sequence up to the block size that we've chosen here, which is 128, has been padded with zeros. And so this is necessary numerically for putting all the tensors into one batch into the model. They all need to be of the same length. And so we pad them with zeros. So now it's a good practice to keep ourselves organized. And let's create a data class that is going to capture all the different variables we're going to, and hyperparameters we're going to use in this notebook. So in particular, there are a number of things that are going to need to capture and write down. The block size, the vocab size, and then some of the parameters for a model. So I'm just going to fill these in right now so we have them. But we'll be using this config object to pull these values, and so we don't have to have them hard-coded or just as loose variables. Okay, so now we have our data set, and now we're going to define the transformer model architecture itself. So again, all this code is available here under the Lecture 3 notebook. This is also the same code that's in the main.py, which is just an implementation of all this in one file that you can use. And so I'm not going to go and type out the whole transformer architecture in this video because it's right here, but we will talk through the different elements of the architecture. So in particular, we'll start with the transformer model itself. So the transformer model consists of input embedding, a series of transformer blocks, and then an output projection. In our case, we're going to build a decoder-only transformer. So the blocks, which are defined here, consist of two main parts. First, the attention, and second, the feed-forward network, with residual connections for both of those. So in particular, we can see that as our information flows through the transformer, we start by embedding it using token embeddings and positional embeddings. We pass it through the blocks and then through the output layer to get the logits. The blocks themselves are defined here. You can see the forward pass through the block consists of first layer norm of the input. The input goes through the attention mechanism. The attention's a causal self-attention, meaning that we use a triangular mask to mask out sort of the future or the next items in the sequence, so the model can't see them when predicting them. This is paired with the input data, again, as a residual connection. Then this goes through the feed-forward network, another layer norm, another residual connection, and that's the output of the transformer block. Our transformer is going to have multiple blocks, and then the output of those blocks is going to go through the output projection to give us the logits over the next token in the sequence. So in particular here, we implement causal self-attention just the same way that is done in neural networks 0 to hero. I think this implementation is fantastic because it is incredibly clear and obvious what exactly is happening. And so because this is multi-head self-attention, the first step is to split our input vector into keys, queries, and values across these different heads, which we use like another batch dimension here. This is just a really clean computational way of doing this. And then we simply transpose the head dimension and the time dimension at the end of these operations. Then we do just vanilla self-attention with the triangular mask. We'll replace this later with flash attention, these blocks here. And then the refined projections then, or the refined hidden states then are passed through the projection, the output projection to produce the logits. And then we do, I think in Neural Network Zero to Hero, there's an explicit implementation of this new GELU. I think there's a implementation of this in PyTorch now, but let's just leave it in here to keep things super consistent. So this is our transformer model architecture. We have, and this is exactly the same model architecture as GPT-2. So everything should be very familiar here. Okay, now that we've defined our transformer model architecture, let's try to initialize a model. So first thing we're going to do is we're going to set the block size and the vocab size in our config using the values from our trained data set. This is just a nice clean way to do this that will make the model work for any input length that we use later. And then we'll instantiate a new transformer model architecture and just take a look. So we have 200,000 parameters here. We can see our model consists of a token embedding, a position embedding, then a series of transformer blocks, decoder blocks, with a final layer norm and a linear projection at the end. So this is again the same architecture as GPT-2. Now, how do we train this model? In order to train the model, we need an optimizer. In this case, we're going to use AtomW. This is just like a very standard optimizer that's used all over the place. It's very forgiving. That's why a lot of people use it. So we'll use that here. We'll create a data loader with our training set, and maybe this is worth just kind of looking at individually here. So once we create the optimizer and the train loader, what good is this? It's so we can get batches out of this train loader. And in particular, this train loader will give us infinite samples at random, as many as we ask for. And the way that those samples are returned is in this very specific format that we've defined previously. So in particular, each batch is going to consist of 32 training examples. And for those 32 examples, we have the vector representing the sequence as X. And we also have a separate vector Y, which is sort of the sequence shifted over by 1. And that's going to contain the values the true values that we want our model to predict. And so we'll use the Y vector to evaluate the loss on the batch. So how do we do this in a training loop? So I've kind of trimmed down this training loop just to make it very simple for this video. This has just the barest elements to it. We'll loop over the training loader to get batches. Again, these are going to be 32 examples. We're going to put each batch on the PyTorch device. This will be really important later when we accelerate the training with MPS or CUDA. It's not super important now for the CPU because the tensors are by default created on the CPU. Once we have our data, we're going to feed it into the model. The model is going to predict the next character at every position. And then we're going to use those positions to calculate the loss because we pass those in as well. Once we have the loss, we can do our backpropagation. So we zero out the gradients on all our parameters. We calculate the gradients with respect, we calculate the gradient of the loss with respect to the parameters. And then we take a step with the optimizer. And so updating all the parameters with the gradients that we just calculated. And then finally, we will do some printing, and then we'll end this loop when we reach max steps in our config. And I believe we set this to 200,000. or no, let's set it to 100 for this just initial run. So let's restart and run this whole notebook. Really good idea to always do that with all your notebooks. You never want to have weird hidden state kind of lingering in Jupyter notebooks. And so we'll run through instantiating the data set, or reading in the file, instantiating the data set, creating the model, and then doing a few training steps with it. So let's see if this is able to train a little bit. Okay, so this is able to train. We just trained it for 100 steps here. And we can see that the loss is sort of starting to go down. So that's probably a good sign. So we've sort of begun to train our first protein transformer model on this data set. Okay, so now that we've verified that this can train a little bit, let's examine what it would look like to generate some sequences from the model. So in order to do this, we follow the same logic as before. We start with a vector of padding character. We use the model to generate the logits for the next character in the sequence. In this case, we're going to scale the logits by a temperature. And from those normalized logits, we get probabilities, which we sample from to generate the next character in our sequence. We do this autoregressively to generate new sequences from our transformer model. And then we have another function here, print samples, which will just help us pretty print this kind of stuff. So let's take a look at what kind of sequences our model, this untrained model, generates right now. Or I should say barely trained. So maybe let's actually look at the completely untrained model first. So let's restart and clear the outputs here. And then we'll just run everything up to the training loop. So I will not run this training loop here, and instead it'll just generate from the model. Okay, so this is the generations from the untrained model. These obviously don't look great, right? They don't look like proteins. We don't expect them to. They don't start with methionine. They're very short, and I mean, you can just kind of look at these and think maybe that's not a great protein, which we'd expect from a completely untrained model. So let's train the model just for a few steps here and see if we can get some slightly better predictions, see if we can at least get it to learn methionine always is a start and that kind of stuff. So we can train just for a few steps here. The loss is starting to go down. That's good. We can hope that the model might at least learn the samples start with methionine. Let's see. Okay, that's good. So just after 100 steps, the model has learned that if it sees 3 dots to start out, methionine is the next character. So that's good. Obviously, this isn't a very useful model yet without any training. We're going to have to train this model to make it useful. But let's see if we have another. Okay. But it's worth just reviewing sort of the steps we went through in this third lecture here, where we implemented the transformer model. So just to go over the notebook again, we start out with some imports. We set our torch manual seed and our random Python standard library random seed. We define a protein data set. This is a data set that enables you to take a FASTA file of protein sequences and feed it into this Python object. And then this Python object will then be able to generate new training examples for your model in a loop. And in particular, what we have is each sequence is represented by a series of integers, and then the predictions are also a series of integers sort of shifted over one. So for every position in the model, we hope that, or for every position in the sequence, we hope the model can predict the next amino acid in that sequence. We play with a little toy data set here, show how the data set class works. Then we wrap everything into a nice function to create our data sets in a reproducible way. We read in our actual data set here, and then we look at some training examples, and we wrap everything into a nice configuration class here. We define GPT architecture transformer model, identical to GPT except for the embedding size and vocabulary. Here in Python, again, this is a very straightforward model, and this implementation from Andre Karpathy's Neural Network Zero to Hero course is just wonderfully straightforward and easy to understand. So we repeat that here. And then we can just show that we can create an optimizer, data loader, train our model for a few steps, and then generate from this transformer model to generate new protein sequences. I don't think any of these protein sequences are wonderful. It's only been trained from 100 steps. But I think the next step would be to train this model for much longer and see if we can start to generate some useful protein sequences. So what I'm going to do now is change the number of steps here in our config. And in particular, I'm going to change this number to 200,000 steps. And I'm going to change this device to MPS so that it'll use the Apple Silicon GPU on my laptop here. And we will give this a run and come back in a few minutes.